the second PUC organic chemistry. We were studying the properties of phenols. Properties of phenols. So earlier we have seen some reactions like the reaction with the sodium hydroxide, etc. Now let us continue the reaction with zinc dust. Okay. So when phenol or any phenolic compound is heated with zinc dust, the reaction that is taking place will be the reduction reaction. That means when you take this phenol, heat with zinc dust plus zinc, right? So you heat, then the oxygen atom will be removed from this phenol so that it gives rise to the benzene. So the product obtained will be benzene plus zinc oxide. Any phenolic compound will undergo similar reaction. Only oxygen atom of the phenolic OH group will be removed. So it is giving rise to the corresponding hydrocarbon. One more explanation I will give you. For example, suppose you take this salicylic acid, OH and COOH. Okay. Suppose it is heated with zinc dust. This is also phenolic compound. When you heat this with zinc dust, only this OH group oxygen will be removed. So it gives rise to the benzoic acid, C6H5COOH. It will give rise to. This oxygen atom will be removed and in place of that hydrogen will be substituted. So any such compound containing OH group directly attached to benzene, phenolic compound, they will undergo reduction to give rise to corresponding lower compound except this oxygen atom. So the next reaction is the reaction with bromine. The next reaction is with bromine. There are two types of reactions in this reaction with bromine. One in presence of aqueous medium, the other one in presence of organic medium. So first let us consider this bromine water. Actually bromine is very less soluble in water. So to prepare this aqueous solution of the bromine, first we have to dissolve potassium bromide in this water. Potassium bromide being an ionic compound, it is highly soluble in water. Once this solution is treated with bromine, bromine easily dissolves. It is because of the formation of the complex, that is KBr3 complex. That's why to prepare the bromine water, first we have to dissolve potassium bromide in water, then add this bromine. So when phenol is treated with bromine water, it gives rise to a product immediately, a white precipitate of 2,4,6-tribromophenol is formed. OH, Br, Br and Br. That is 2,4,6-tribromophenol. Usually it is indicated with 2,4,6-PBP. Since 3 molecules of bromine will undergo reaction, the other product is 3-HBr. It is a nuclear electrophilic substitution reaction in which benzene ring undergoes substitution with bromine. Remember, when bromine is dissolved in water containing potassium bromide, it is highly polarized. That's why that nucleophilic attack, electrophilic attack will be more easy. That's why all the 3 positions will be substituted. But when we use this bromine in carbon tetrachloride or CS2, carbon disulfide as a solvent. Carbon disulfide, carbon tetrachloride, they are all the non-polar solvents. So bromine will undergo reaction only at either ortho or in the para position. Bromine in CS2 will give rise to 2 products, mixture of 2 products, OH and Br in the ortho position plus OH and Br in the para position. So this is ortho, this is para bromophenols. Along with these 2 molecules of HBr will be eliminated when we take 2 phenol and 4 bromine molecules. So this is with the bromine water. The reaction with nitric acid with HNO3. Again there are 2 reactions in presence of the nitric acid. One with dilute HNO3. When we dissolve this nitric acid in excess of water, phenol gives rise to HNO3 in water, gives rise to same type product, that is orthonitro, OH and NO2 plus OH and NO2 in the para position. This is ortho, this is para, nitrophenols. Nitrophenols. Remember, especially this reaction with bromine water, it is so fast that its velocity or rate of reaction can be compared with inorganic reactions. Because of the presence of the polar bromine molecule in this water, it undergoes a reaction easily. As soon as you add bromine water to this phenol, a white precipitate of bromine 2,4,6 tribromophenol is produced. So this can be used in the laboratory to test the phenol also. When phenol solution is treated with bromine water, it gives a white precipitate of 2,4,6 tribromophenol. Along with that, bromine pink color or brown color of orange color of this bromine is disappeared. With the nitric acid, dilute HNO3. Phenol reacts to give rise to ortho, nitro and para nitrophenol. But when you take this nitrating mixture with concentrated HNO3 and concentrated H2SO4, this mixture is named as the nitrating mixture. Phenol reacts with HNO3 in presence of concentrated H2SO4 to give rise to 2,4,6 trinitrophenol, NO2 and NO2. Remember, we are writing this NO2 so that the nitrogen links to this benzene ring. Don't write NO2 and write this to benzene ring. Link this to benzene ring. No, it is not correct. So we have to link nitrogen atom to this benzene ring and it gives rise to 2,4,6 trinitrophenol. This is also named as picric acid. Picric acid. This is named as acid because its acidic strength will be very, very large. We can compare the acidic strength with concentrated HCl. We will discuss about the acidic strengths in the later part of this topic. So whenever phenol is treated with nitric acid, it will undergo reaction at all the 3 positions, 2 ortho and 1 para position, to give rise to 2,4,6 trinitrophenol, picric acid. So this picric acid can be used as a laboratory test reagent for the detection of the potassium radical. While we do the analysis of inorganic salts, basic radicals, then we use this picric acid as a dilute solution to detect the potassium radical. And also in the concentrated or the solid itself can be used as an explosive. Most of the nitro compounds of the aromatic ring, attached to aromatic ring, they are used as the explosives. So with concentrated HNO3 it gives rise to 2,4,6 trinitrophenol. With dilute HNO3 it gives rise to orthonitro and para nitrophenols. So this is about the reaction with concentrated and dilute HNO3. The next reaction is with formaldehyde. With formaldehyde. With formaldehyde, this phenol reacts with formaldehyde to give rise to a polymer called as the bakelite. Bakelite, it is a phenol formaldehyde polymer. Actually, it is a 3-dimensional polymer. That we will discuss in the polymer chapters. Okay, chapter. Actually, formaldehyde will undergo substitution in the ortho as well as para positions. Okay, this HCH2OH group, it is called as the methylol group, will undergo substitution in the ortho and para positions. So such groups will further undergo dehydration reactions to give rise to a three-dimensional polymer called as the bakelite. The next one is with concentrated H2SO4. With concentrated H2SO4. The reaction takes place giving rise to different products under different conditions, especially temperature conditions. When we take this phenol, react with concentrated H2SO4 at 280 Kelvin. 280 Kelvin is just 7 degrees Celsius, that is under cold condition. It will give rise to ortho phenol sulfonic acid, OH SO3H. This is ortho phenol sulfonic acid, benzene sulfonic acid. Benzene sulfonic acid. But when the same phenol is reacted with concentrated H2SO4 at 370 Kelvin, at about 97 degrees Celsius to 100 degrees Celsius, it gives rise to para substituted, this is ortho substituted SO3H. This is para substituted OH and SO3H. This is para phenol benzene sulfonic acid. Benzene sulfonic acid. We can also name these compounds as orthohydroxy benzene sulfonic acid. Orthohydroxy. This is para-hydroxy benzene sulfonic acid. But the thing is, once we heat this ortho to about 370 degrees Celsius, 370 Kelvin temperature, again this ortho is converted to the para. This is actually migration of the SO3H group to give rise to the para product. In the ortho position there is a steric hindrance. That's why it will easily undergo migration to the para position at 370 Kelvin temperature. The next one is with nitrous acid. With nitrous acid. Actually nitrous acid is not available because HNO2 is highly unstable. That's why we will consider this reaction by taking this sodium nitrite and HCl. When we write this phenol react with this nitrous acid HNO2. So to get this HNO2 we have to take NaNO2 and HCl mixture at ice cold condition. This will undergo reaction to give the substituted product in the para position. Para-nitrosophenol. This NO group is named as the nitroso group. Para-nitrosophenol. Whenever we substitute nitro groups or nitroso groups, the compound will have the yellow color. It is because of the nitro group or nitroso group that is responsible for the yellow color. So this para-nitrosophenol is also an yellow compound. So this is about the reaction up to with the nitrous acid. We will consider some more reactions in the next video. Thank you.